Swayam Prabha. Digital India. Educated India.
Welcome everyone to this NPTEL online certification course on techniques of materials characterization. So, we are beginning with module 11. We are almost close to the end and we are discussing with X-ray diffraction. We will be continuing with X-ray diffraction for this module and the next module, which is the last one. And we were in the last module onward, we were discussing about intensity of diffracted beam, and we will continue with that. At least for this module, we will be discussing about the intensity of diffracted beam. So, what we will be discussing now is basically, in the last module we started discussing about intensity, and there we have seen the importance of arrangement of atoms in determining that what diffracted beam, even after diffraction, even after Bragg's law is satisfied, whether we will be getting any intensity from that after diffraction or not. That is somehow related to the atomic arrangement within the unit cell or within a crystalline material. So, we started from there and then we try to derive some kind of expression which will be relating this which will be expressing this relationship between the structure of a atom or arrangement of atoms in a crystalline materials with the diffracted beam, the intensity of the diffracted beam that is coming out of the crystalline material. So, in that way we started, and we what we find out is that we have to start from very basic, how the X-ray is interacting with an electrons, individual electrons in an atom. First we have to start from there, and we discuss there and we find out two different type of interactions. One is the Thomson effect, one is the Crompton effect, and we just considered Thomson effect because that is what is important for calculation of diffracted intensity ultimately, but Crompton modified radiation was also important. We discussed about that how it modifies the background and so on, and from there after the electron, what we considered is the intensity of the diffracted beam coming out of an individual atom. So, how the different electrons, so individual atom that contains different type of lots of different electrons, and how we can superimpose all the waves along certain direction, how we can add them up depending on their phase relationship, depending on the amplitude and so on. And then we discussed about a factor called atomic scattering factor. We defined that, we saw that what it depends on and how it is helpful. So, from there what we just started in the last class was the relationship, establishing a relationship between the intensity of diffracted beam and atomic arrangement, and there we were just tried to understand the phase relationship between the diffracted intensity or diffracted beam or the waves coming out from two individual atoms. One is kept at the origin and another one is kept arbitrarily in somewhere in the space. So, that up to there we discussed. We will continue that this week as well, this module, at least this lecture we will continue with that scattering by an atom, scattering within the unit cell, and then we will discuss about something related called the structure factor and how the structure factor is calculated. Okay. So, this part we all discussed, the scattering by an unit cell we have seen depending on these two different type of unit cell, how the intensity or diffracted beam is present for one set, the one particular type of intensity diffracted beam 001 or 100 diffracted beam is present in base centered and it is not present in the body centered one. So, that means definitely some atomic arrangement has something to do with the diffracted beam intensity. We realized from here, and even though the Bragg's law is satisfied for both conditions, in one case we get an intensity and another case we did not get an intensity. And from there in the last class we derived this relationship, we did all of this, I am just repeating it again. What we did is basically we imagined an atom in the origin and then we imagined another atom somewhere at a distance of x, somewhere in the x direction, and we imagine that Bragg's law is satisfied for this H00 type planes here, and so this two atoms, this one and this one, the A and C, definitely there the phase relationship is an integral multiple of path difference. So that is true if Bragg's law is satisfied. Then we imagine another type of atom situated at a point B, and then we try to find out that along this same direction, that means the same for the same incident angle, same where Bragg's law is satisfied, the theta angle, how we can superimpose this to, or how we can add the waves that is coming out, X-ray waves that is coming out from this A atom and this B atom, which is arbitrarily oriented somewhere in the space, and here in this case at a distance of x along the x direction. So, then what we find out finally is the phase relationship, and that is given between the phase relationship or the angular phase difference between this the wave coming out of this A atom and the wave coming out of this B atom. The phase relationship we finally find out. First we calculated the path difference, from there we calculated the phase difference, and that phase difference is coming out to be 2 pi h x by A, and then we take the fractional component, that is A is the lattice parameter here. So, the fractional component of this position of this B atom, that is given by x by A. So, finally what we find out is the phase difference is 2 pi h into u. H is here denoting, remember this, H is here denoting these planes which are satisfying the Bragg's condition. That means the diffraction is happening from which plane, that is denoted by this H, and this u here is denoting the position of this second atom, arbitrarily chosen second atom. So, up to here we discussed in the last class, and today we can extend this. I am not going into a detailed derivation of this entire part, but what we can do is that we can check this, this reasoning, the same kind of calculation we can extend it all the way to a 3-dimensional network, where we can imagine that along the origin there is one set of plane is going, and then we can imagine another set of plane arbitrarily anywhere in the space, which is making again a fractional coordinates of x, y, x a, y b and z, z, z c. So, this is this atom, instead of atom now we are considering a complete plane here. So, in this plane which is having a coordinates of x, y, z and fractional coordinates, if we imagine that the lattice parameter for this unit cell is a, b, c, then the fractional coordinates for this arbitrarily defined plane is x a, y b, z c, or otherwise we can write what we can write here very straightforward. We can write something like u similarly x by a and v is given by y by b, and we can write that w equals z by c. So, this is the fractional coordinate of this arbitrarily defined plane. So, for this arbitrarily defined plane, now what we can write, the phase difference between the rays coming out of this plane, the phase difference from the rays coming out of this plane and this another arbitrarily defined plane. The phase difference between them we can extend it into 3 dimension, and we can write that in this way, simply 2 pi h u plus k v plus L w, where h k l is basically this plane, this arbitrarily, this origin, this plane h k l, and for this h k l plane the diffraction conditions are satisfied, and this h k l plane is basically diffracting in the diffracting condition, that is what. So, this basically this term is giving the phase difference between the origin or atoms present in the origin or the planes passing through the origin and any other arbitrarily defined plane. So, that is a phase difference between the X-rays coming out from these two atoms or atomic planes. Now, one thing we must understand is that this relation is very general, and it is applicable to any kind of unit cell of any shape. There is no restriction, because everything is arbitrary here, A, B, C. Lattice parameters, what is their angle, we did not define anything, that angle can be anything, that relation between A, B, C can be anything. That means, this unit cell can be any one of out of the 7 crystal systems or 14 Bravais lattices, anything. And but for all of them this relationship will be valid. That means, this unit cell, this relation is completely general. Okay. So it can be valid for anything. Now the point is that this relation, these two waves, the waves that is coming out of this plane A and the wave that is coming out of this another atom B, and they not only differ by on this phase difference, but they can also have an amplitude difference, okay, and that amplitude difference will be the same, the amplitude will be the same if they are same kind of atom, that is okay, that is fine. If it is composed of a single element, let us say I am considering something like iron, so every atom is iron and this is I mean like the amplitude of the waves coming out will be the same for all, but in case this is a multi-element component, a multi-element system, let us say I have iron as a one and aluminum as the other one. So, these two types of atoms are composing this entire unit cell. Then I have to consider their amplitude separately, and amplitudes are normally, as we already understand, from individual atom, the amplitude is basically nothing but the F, that atomic scattering factor, appropriate values of atomic scattering factor. Why appropriate values of this? Because we know atomic scattering factor depends on sin theta by lambda, this term. So, an appropriate value of atomic scattering factor will define this amplitude of these two waves. So, not only the phase difference we have to consider, we also have to consider their amplitude, and that amplitude is given by the atomic scattering factor. So, if it is composed of two iron and aluminum, then these two X-rays will contain two different waves, and one of these waves will have amplitude of this FFE and another one will have FAL with a phase difference of phi between them. Okay. So, now simply we can imagine that the problem has become, this entire problem of scattering from unit cell is now comes down to a problem where we have to just add up these two waves. As I already said, two waves we have, let us imagine that we have one wave with F1, one wave with F2 and a phase difference with phi. So, this we have to just add them. This is the entire problem for the entire unit cell. This is what will be telling us, or this is what we will be giving us the diffracted wave, the intensity of the diffracted wave, the amplitude, phase, everything. If we just add up these two waves, and these are completely arbitrary, two different arbitrarily defined atoms for any kind of unit cell. Okay. So, this is completely general, fine. So, that means basically we have to add up this wave scattered by the atoms in the unit cell, one in the origin and another one somewhere else. This summation, the best way of doing this summation is by expressing these two waves in terms of a complex exponential function. So, we will see what basically means by complex exponential function and all. What we can do is that we can represent, first of all we can represent these two waves. Let us imagine one of the waves is coming out of the origin, one of the waves is coming out from this arbitrarily defined plane, any atom from this arbitrarily defined plane. We can represent this two waves by the variation in their electric wave, electric field vector, electric field intensity, because if you remember we already said that every wave these are electromagnetic waves. So, they can be represented by their electric field vector, and that electric field vector continuously sinusoidally varies with respect to the time for a fixed position and with respect to position for a fixed time. So, we can imagine these two waves as these two sine waves basically where their electric field vectors is varying with time, and then we can add them up and get the resultant wave. So, the way we can possibly express these two, we can express one of these is like this, where we have this A1 into sine, these are both we are expressing basically these two, one is this E1, both of them are sine waves, okay. One is this and one is this, both of them are sine waves. So, we are just writing their expressions, okay. So, what we can write here is 2 pi nu, this is not actually, this becomes almost like a gamma, this is not gamma, and this is basically we have to write nu, okay, just give me, okay, nu t minus phi 1, and the second wave we can write it in this way, 2 sine 2 pi nu t minus phi 2, okay. So, these two waves has exactly the same frequency, that means same frequency, or for that matter they have the same wavelength, fine. Both of them have the same wavelength, these two waves, and they have to have same wavelength, because then only they will be able to, they can be add up, these two waves, they can be added up. But they differ in the amplitude and in their phases. One is having phi 1, one is having phi 2, and ultimately if we add them up, we will get this third one, E3, third wave E3, which is again a sinusoidal wave, but this time with a completely different amplitude and different phase in itself. Okay. This will be a resultant wave of out of these two waves. If we sum them up at any given position, any given point, if we sum them up, we will be getting this third one with its own phase and amplitude, which is of course related to the phase and amplitude of these two waves that we define. So, we have to now basically find out this third wave, this E3, that wave, that will be the resultant final diffracted intensity coming out of this unit cell, complete unit cell. So, one way we can do that is basically by expressing these two waves as vectors. Okay. So, these vectors, basically what we can do is that we express the vectors in the plane in this vectors, this vector addition waves, which is, I think everyone knows the way we can express one of these waves. We can think about the length as their amplitude, and the angle is related to the angle they makes with the x axis. This here, this is basically the angle is the phase angle here. This is their phase angle, this is another wave, this is the amplitude, and this is the phase, and then the third wave or the resultant wave is basically this with an angle pi 3, phase angle pi 3, and we can just find out this resultant wave from simply adding these two vectors by following the parallelogram law. Okay. So, this is one way we can very easily find out the resultant wave out of this. Okay. This is a little tricky to do it, and we cannot find out the general expression so easily. So, we will do it, we will solve this problem in some different way altogether. Basically, this geometrical construction, this vector construction, we can avoid it by some analytical treatment by using complex numbers. So, we can bring this complex geometry here, the complex numbers we can bring it here, and then we can do this adding the same summation, we can do it in a much simpler way. Okay. So, how we can do that? That is what we will be seeing now. So, complex numbers, as we know that this numbers, complex numbers are plotted in same way as the vectors, we can plot them in this complex plane, where again the amplitude is represented by the amplitude, yeah. So, amplitude is represented by this length of this, and this is the given this and this angle that it makes with this real axis. The real axis is this one, this is the real axis here, and abscissa is the real axis, this one, and this is the imaginary axis. This y axis is basically the imaginary axis. Complex numbers, you know, they are expressed by this way, a plus b I, that is I is root over minus I. So, I is basically having a value of root over minus 1, which is the imaginary part of this entire expression. Okay. So, in this complex plane, if we express any of these waves here, now the amplitude is again just like vectors, the amplitude is represented by this length, and this angle with abscissa, this x axis, this is angle is the phase axis, that is it. So, here now what we can do is that this vector, we represent this one vector in this complex plane, and then we can try to sum them up. Okay. And that we can do it in this way. Basically, here we represent the waves in by this amplitude, that same wave. If we imagine that E equals A into the way we have expressed them earlier, E equals sine 2 pi nu t, minus phi. This is the general expression that we earlier wrote for this this waves that is coming out from each of these planes or each of this set of atoms. So, we can represent them in this complex plane here itself, and similarly now we can add them up using this complex number. So, what we can do here is that by each of these waves we can express them in this way, that is, we can express them by a power series expansion, where we can write this as basically equals A into cos phi plus I sin phi. So, this is how we can express any of these waves, any wave in the complex plane, we can express them in this term as a power series expansion, where we have this cos phi and sin phi. Basically, cos phi and sin phi, if this one is the wave in the complex plane, then cos phi and sin phi are the two components along the x axis and y axis. That is how we basically express them here in the complex plane. Any wave we can express them here in the complex plane, and simply we can, the intensity of the this waves, we know the intensity is basically its square of the amplitude. So, what we can get the this intensity of any wave just by multiplying this wave, this wave by its complex conjugate. So, what do you mean by complex conjugate? Basically, if any of this, any wave is expressed by this, then its complex conjugate will be A E minus I pi. So, this is the complex conjugate of this wave, and if I multiply this two, that means what I can do is that I can write A E I pi, just the modulus of it means the absolute value of it, we can multiply it, we can imagine it in this way, into A E minus I pi, and this equals to A square, because I square, we know I square equals 1 basically, okay. This is I, and if you square it, this will be minus 1, sorry, this will be minus 1, I square will be minus 1. So, this basically finally comes out minus I square, which is again the 1, and finally this is how we can get the intensity of this wave simply from this by multiplying it with its complex conjugate. So, what we now basically the way this part, the importance of this part is to make you understand that any wave in the complex plane, same wave, the waves that we were talking about in the earlier cases here. So, one wave coming out of this origin and one wave coming out of this arbitrarily defined plane anywhere from this plane. So, these two waves we can just represent them either as a vector here, or we can represent them in this way as a the sinusoidal waves, and then find out the third one. We can represent them in the vector as a vector here, and then we can find out this using the parallelogram law, we can find out the third one, the resultant vector. Or the simplest way of doing it is by imagining them as a complex number in the complex plane, and then try to see how they sum up. So, that is exactly what we are trying to do here. Okay. So, now, so when we do this addition, adding the scattered wave from each of the atoms in the unit cell, this when we do is basically requires the addition of this complex numbers representing this amplitude and phase of each of these waves, that is what. So, one of these waves, as we understand, these waves are represented by this is the expression for each of the wave, and then one wave coming from the origin, one wave coming from any other atom, any atom situating anywhere else, and we just add them up, as we said the amplitude, and we have to just add their amplitude and the phase. So, amplitude is given by the appropriate value of atomic scattering factor. We have already seen that atomic scattering factor, if we have two different one, then we can write two different atomic scattering factor. If we have one single type of element, we can write one single atomic scattering factor, and we have to find out the appropriate value of this atomic scattering factor considering the sin theta by lambda. That means, if we know, if you understand this 2d sin theta equals lambda, that means basically what we can write, what we can write here is sin theta by lambda is basically 1 by 2d. So, this we can find out exactly for which sin theta by lambda this atomic scattering factor is valid. So, we have already seen the relationship. From there we can calculate this atomic scattering factor of any particular sin theta by lambda, means any condition, particular Bragg's condition where the diffraction condition is satisfied. For that, what should be the atomic scattering factor. So, these two we can find out for a single element, the f will be the same. Okay, and phase, we have already seen that the phase difference is given by this expression 2 pi h u plus k v plus L w. So, this is the phase relationship between them. So, the resultant wave that is scattered out of this entire unit cell, this we can the final one we can write it in this way, that is F, which is the final resultant wave that is coming out of the entire unit cell. We can write down that as a summation of, basically if we imagine that there are n number of such atoms. Okay. If we imagine n number of such atoms, we can calculate this, n equals to 1 to capital N and E A I pi. So, this is individual, or rather what we should write it here, this we can write, make it a special and write it as A N E I Q pi N. So, this one is the general wave and we are just summing it over all the atoms present in the in that unit cell, and that is giving me the final expression for ultimate expression for this diffracted beam coming out of this unit cell. Okay. So, this we can write it as again summation of n equals from 1, if it contains capital N number of atom, then we can write it, if we imagine that it is one type of element, then we can write it as E into 2 pi I, and for phi we can write this expression, E is plus k v plus L w. This is the final expression. So, this expression is the final expression for the diffracted intensity, diffracted beam intensity coming out of the unit cell, and this is called, this is the resultant wave. Basically, this is the resultant wave from coming out of all the atoms in the unit cell. This one, this F is called the structure factor, because it describes how the atomic arrangements which is given, the atomic arrangement for in the unit cell which is given in terms of U, V, W, how this atomic arrangement is basically affects the intensity of the scattered beam for a HKL diffraction. So, HKL diffraction is happening for HKL planes, which is for have a fixed sin theta for a fixed lambda. This how this diffracted beam intensity is getting affected by the atomic position U, V, W. So, that is given by this structure factors, and we calculate the structure factor by adding up all the waves coming out from individual atoms in a unit cell. So, this is the final structure factor expression that we can calculate. Okay. So, this is basically the structure factor is a complex number and it expresses both the amplitude and phase of the resultant wave. So, what we can write is that if we have, let us say, two different type of atoms in this in the unit cell, we can write first one is having an amplitude, that is atomic scattering factor F1, and if it is, it has the fraction of like U1, V1, W1, then what we can write from this expression, basically what we can write is E raised to the power 2 pi, and we are satisfying something like HKL diffraction is happening. So, HU1 plus K plus K V1 plus L W1, okay, plus for the second atom we can write like this, if that has a fraction this of fractional coordinates at U2, V2 and W2, we can write this. So, by adding these two we will be getting the final structure factor. Okay. So, structure factor in general it is a complex number, just like any wave can be expressed by this term. Structure factor also can be expressed by this one. We have already seen structure factor is basically expressed as a complex number which is a summation of this all n number of waves which are present from individual atom which are coming with different amplitude and different phases. So, structure factor can be expressed in terms of a complex number like this. Okay. And the mod, that is the absolute value of the structure factor, basically gives the amplitude of the wave scattered by this entire unit cell. So, this the mod of this, that means this structure factor, we can go back to the laser point again. So, the structure factor is given like just like the atomic scattering factor, structure factor can also be given or can be defined as the ratio of the amplitudes, and structure factor, the way we define it is basically the wave scattered by all the atoms in an unit cell divided by the amplitude of the wave scattered by one single electron. So, in that respect, structure factor is basically n times the absolute value of atomic scattering factor. Atomic scattering factor, you know, the way we define it is basically the amplitude of the wave scattered by one single atom divided by the amplitude of the wave scattered by one single electron, whereas structure factor is the amplitude of the wave scattered by all the atoms if the unit cell contains n number of atoms. So, simply we multiply the atomic scattering factor by n and we get the absolute value of structure factor, provided the unit cell containing only one type of atom. So, this is how the structure factor and atomic factor basically are related, and this is how we can also define the structure factor or the amplitude, the absolute, not basically the structure factor, but the value, the absolute value of structure factor we can, because here this is the amplitude of this complex, this wave of that is defining the structure factor, the amplitude of the wave coming out of the unit cell, that amplitude we can define that amplitude in terms of amplitude of wave scattered by one single electron. And the intensity of the beam diffracted by all the atoms is predicted by Bragg's law, and the intensity is simply proportional to f square, which is the intensity that as I said that okay, you can go back to the pen. So, the final intensity is simply the square of the modulus of this amplitude of the beam. Amplitude is basically this, as we just now discussed, the amplitude is given by mod f and mod f square. This is what the amplitude, and this mod f square we get by multiplying again f with its complex conjugate, which is represented like this, and which we can say is, again it is expressed as minus I phi. So, if we multiply f with its complex conjugate, what we get is this intensity of the diffracted beam coming out of the entire unit cell. So, the structure factor, the dependence or the importance of the structure factor is calculation is that this is a very important relation, and it permits a calculation of the intensity, final intensity of the diffracted beam coming out of a unit cell of any shape, unit cell of any kind of a crystal system. The intensity of the diffracted beam for a particular h scale deflection means for a particular h scale set of plane, if they are satisfying the diffraction condition, what will be the intensity of the final diffracted beam irrespective of any kind of crystal system we can calculate simply by calculating its structure factor. So, this is what is the importance of structure factor, and this is where we will stop for this, and we will continue with structure factor calculation for some specific crystal systems in the next class. Thank you.